So now let us try to apply the C-line method of finding the stresses being experienced by a concrete element in a sample problem. So actually this sample problem is similar to the previous problem. So we just change some of the information on the problem. So we have a pretension simply supported 10 LDT24 double T-beam without topping, which looks like this in actual, which has a span of 19.51 meters or 64 feet. So the length of the double T-beam is equal to 19.51 meters. And the geometry shown in the figure. So later we will show the actual geometry of the cross section of the double T-beam. So it is pretension and has a tendon profile like this, which is called Harp tendon profile or harping, usually used for pretensioning, while for post-tensioning, we usually use parabolic tendon profile or drape tendon profile. So it looks like a parabola. So for harping, or for harp tendon, it looks like this. And for the drape tendons, it looks like a parabolic curve. So this is the simply supported beam. So it has hinge support and roller support at ends. And this is the centroid of the cross section. So the eccentricity of the pre-stressing reinforcement, let us just call that eccentricity all throughout the length of the beam as eccentricity E with a magnitude of 375 mm at the center and 197 mm at the ends. And the self-weight of the retention beam is actually given as well, equal to 5.24 kilonewton per meter. So it carries its own weight. And additional to that own weight, it is subjected to a uniform superimposed gravity dead load intensity WSDL and live load intensity WLL, summing to 6.13 kilonewton per meter. So the sum of the WSDL and the WLL is equal to 6.13 kilonewton per meter. So the initial stress before losses is equal to 70% of the ultimate strength of the pre-stressing reinforcement. And then we all know that after that pre-stress force is transferred to the concrete element, the pre-stressing reinforcement will experience what we call pre-stress losses and will have a reduced pre-stressing force or pre-stressing stress equal to the effective pre-stress after the losses have occurred, which will be equal to 1034 megapascal according to the problem itself. So the problem asks for the extreme fiber stresses at midspan here due to the final service load conditions when the pre-stress losses have taken place. So according to the problem, assume that the pre-stressing reinforcement is composed of 10 diameter 12.7 mm 7 wire strand tendons with a 108-D1 strand pattern, which is used on the pre-stressing operations. So the problem specifically specify a particular method on finding the stresses acting on the concrete element, which is the C-line method. So other information about the problem is, or are this, the 28-day compressive strength is equal to 41.4 megapascal. The compressive strength at transfer is equal to 33.1 megapascal, which is obviously less than the compressive strength, the 28-day compressive strength, because again, we all know that the transfer of the pre-stressing force to the concrete element usually occurs even before the concrete attained its 28-day compressive strength. And then the ultimate strength of the pre-stressing reinforcements is 1862 megapascal, and its yield strength is 1,517 megapascal. And also given with the problem, since the problem uses diameter 12.7 mm, so diameter 12.7 mm 7-wire strand actually has 99 mm squared of cross-sectional area, nominal cross-sectional area. So this is the actual cross-section of the concrete element. The total cross-sectional area is equal to 2897 centimeters squared. And if this is the neutral axis, the moment of inertia about that axis is 935,230 centimeter to the fourth. And because the moment of inertia is given only on this with respect to this neutral axis, because we all know that the simply supported T-beam will just bend with respect to this neutral axis. So given that location or given that neutral axis, the distance from that neutral axis to the extreme bottom fiber is equal to 451 mm. And with that, the remaining distance here from the neutral axis to the extreme top fiber is equal to 158 mm. And given the C and the moment of inertia, we can compute for the section modulus, 20,713 cubic centimeter for the bottom fiber, and for the top fiber, 59,108 cubic centimeter. So actually, this information here are given on the problem, so you don't have to compute this. Usually, the geometric properties of a cross-section is usually given on the problem. Although if it is not given, you can compute them using the specified dimensions of the cross-section. So in this case, the total width of the flange is given as 10 feet, and then the thickness of the flange is 2 inches, and the distance between the webs uh, is equal to 5 feet, and then the width of the web on the bottom is equal to 3 and 3/4 inches, and the total height of the cross-section is equal to 24 inches, and the width of the web, the top portion, the upper portion, is equal to 5 and 3/4 inches. And the cross-section actually supports a concrete topping which has a 2 inches thick. Actually, the concrete topping is where the superimposed dead load came from. But according to the problem, the sum of the superimposed dead load, which is composed of the concrete topping, and the live load that will be carried by the concrete beam here, that will be carried by the concrete double T beam, will have a sum of 6.13 kilonewton per meter. So the additional service loads will given are already the sum of the superimposed dead load and the live load. So without further ado, let's start the solution for finding the extreme fiber stresses at the midspan at final service load conditions. So we have to recall, since we are using C-line method, we just have to recall how to find the total stresses acting on the concrete element on using C-line method. And as we have discussed before on the previous slides, we have seen that the total stress acting on the pre-compressed fibers uh, are equal to this formula. And for the case of the pre-tensioned fibers, which is usually below the centroid or the neutral axis, with respect to a simply supported beam, the formula is this. So according to these formulas, if we know the magnitude of P and the magnitude of E prime, we can already solve for the total stresses at the pre-compressed and the pre-tension fibers, since all of the other parameters given here are already given. So we just have to recall, since we are analyzing the concrete element at final service loads, we have to recall that for on the service load condition, which is the one of the stages of pre-stressing, we have to recall that the P or the pre-stressing force acting on the pre-stressing reinforcement at service load condition is equal to effective pre-stressing force PE, which is the product or the result of uh, reduction of the initial pre-stressing force due to the losses. So again, later on the next chapters, or chapter, we will study more about those reasons why the pre-stresses losses occur on the pre-stressing reinforcement. And additional to that information, we know for a fact that for a safe on the service load condition, the moment being carried by the concrete element is the total moment due to the dead load or the self weight itself, and the superimposed dead load and the live load. And if you can remember, on strength of materials or mechanics of the form of all bodies, the formula for the relationship of stress, force, and area is equal to stress is equal to force over area, or if we will express it in terms of the force is equal to stress times cross-sectional area. So we can use that formula for us to find the effective pre-stressing force. So expressing that relationship in terms of the effective pre-stressing force PE, it will be equal to the stress, which is obviously the effective pre-stress that occurs or being experienced by the pre-stressing reinforcement, which is given on the problem equal to 1034 megapascal, and the total cross-sectional area of the pre-stressing reinforcement, which is 10 diameter 12.7 mm 7-wire strand, which has a cross-sectional area of 99 mm squared. So we just have to substitute all of those values here to find the effective pre-stressing force. So this is the effective pre-stress given on the problem, and this is the total area of the pre-stressing reinforcement, 1099 mm squared. So the total area of the 7-wire strand, one 7-wire strand is equal to 99 mm squared, and since there are 10 of those, so we have to multiply it by 10. So again, the product you will get here is obviously in terms of Newton, but again, I just rather chosen to express it in terms of kilonewton. So I hope you already know how to convert Newton to kilonewton. You just have to divide this product by 1000. So there we already found the value of the effective pre-stressing force. So next value we have to find is the magnitude of E prime. But we all know that the formula for E prime is equal to M over P minus E as derived before. So we need to find the magnitude of M, which is the total moment due to the dead load or self-weight itself, the superimposed dead load, and the live load. And since we are considering the section at midspan, we must find the magnitude of moment acting at that particular location, which is the midspan. And we know for a fact that the formula for the moment acting on midspan of a simply supported beam is just equal to W L squared over 8, wherein our W will be equal to the uh, weight of the concrete itself, which is equal to 5.24, and the sum of the superimposed dead load and live load, which is given on the problem, which is equal to 6.13. So that is our W, and then our L, our length is equal to 19.51, which is given on the problem. So if you will compute for that value, the moment acting on the midspan, you will find this value, 540.98 kilonewton meter. So now, since we already know the M, and since E, the eccentricity at midspan being considered is given also, we can already compute for the value of E prime, which is the distance of the total compressive stress with respect to the neutral axis or the centroid, which is equal to this formula, M over P minus E, wherein the M is equal to this, P is the effective force, which is this, and E is the given eccentricity here, 375 mm. So just be careful to have a consistent units. So since the moment is in terms of kilonewton meter, and the uh, force, the P, is in terms of kilonewton, so the kilonewton will be cancelled. Only the meter will be retained. So you have to express the eccentricity E in terms of meter so that you will have a consistent units. So therefore, we can see that the E prime, the distance of the total compressive force with respect to the neutral axis, is equal to 0.15348 meter, or again we just change it to mm, So we just have to multiply it by 1000. So again, I hope you already know how to convert units. And the result will be 153.48 mm. So there, since we already know the value of P and E prime, we can now already solve for the total stresses acting on the extreme top and bottom fiber of the concrete element at midspan. So again, we just have to substitute all of those values that we have computed. So P is equal to this. So again, for consistency of units, I just express every force in terms of Newton, every area in terms of mm squared, every eccentricity or every distance in terms of mm, and the moment of inertia in terms of mm to the fourth. So that the resulting stress will be equal to Newton per mm squared or megapascal. Newton per mm squared is equal to megapascal. So this is P. Just substitute it here. Cross-sectional area given, moment of inertia given, distance from the centroid to the extreme pre-compressed fiber is equal to uh, 153.48. I mean 158 given in the problem. And E prime, as we computed a while ago, it is equal to 153.48. So actually, you can just copy that equation to find the stress at the extreme pretension fiber. So you just have to change the sign here from negative to positive, and then don't forget to change the value of C. Since for the extreme pretension fiber, its distance from the neutral axis or from the centroid is equal to the 451 mm given on the problem. So if you will compute these expressions or equations, you will find the total stresses acting on the midspan of this concrete element at service load conditions. So you can see here that the total stress acting on the extreme precompressed fiber here at the top is a compressive stress, while on the extreme pretension fiber acting on the bottom is a tensile stress. So before you accept those answers as the final answers, you have to check first if they are complying to the provisions of our code. So if you will refer to our code ACI 318M-14 section 24.5.4.1, you can see this table. Or if you will refer to our local code NSCPC 101-15 section 424.4.1, you can also see similar table. Although you have to take note, there is a little bit of typographical error from our local code NSCP, because you can see here that the expression shown is equal to 0.45 FCI prime. So this is in terms of FCI prime, but supposedly it must be in terms of FC prime because we are already in service load condition. So according to the code, at service load condition, the limiting compressive stress on the concrete itself must not exceed this values given here on this table. For pre-stress plus sustained load must not exceed to 0.45 FC prime, and for load condition of pre-stress plus total load, it must not the compressive stress acting on the concrete element must not exceed 0.6 FC prime. So you have to use FC prime. So again, take note of that typographical error from our local code. You must not use the initial pre-stress, the initial compressive stress of the concrete, since we are already in the service loads wherein the concrete already attained its 28-day compressive strength. So the additional the additional service loads, which are the superimposed dead loads and live loads, are just being carried by the concrete element after it attained its 28-day compressive strength, and after it also experienced pre-stress losses on the pre-stressing reinforcement. That's why we are using the effective pre-stress force here. But the question here now again is, which of these two limits will we use on this? So again, we are just considering the dead load, self-weight, the superimposed dead load, and the live load. So we are not computing or investigating on the effect of the pre-stressing force, and the total load, which will include the wind load and the earthquake load and the other load that have to be considered to be carried by the concrete element. So we will not use this part of the table. Rather, we will just use this first row of the table, which is the pre-stress, which is the load condition, pre-stress plus sustained load, since the concrete element just supports the sustained loads of service loads equal to the superimposed dead load and live load, and together with the self-weight itself. So if you will compute for the 0.45 FC prime, give FC prime is given on the problem, and the 45% of that FC prime is equal to 18.63 megapascal, which is obviously greater than the actual total stress we computed here on the pre-compressed fiber, extreme fiber. So therefore, since it is less than on the limit specified by the code, therefore it is okay. So we can accept it as the final answer, the total stress acting on the extreme pre-compressed fiber at the top. So next is we can see here that the stress acting on the extreme pre-tension fiber is a tensile stress. So if we want to check it, if it is compliant with the code provisions, we have to check the permissible stress or permissible tensile stress limit specified by the code at service loads. So you have to check again the limits given by the code. So if you will refer on again ACI 318M-14 section 24.5.2.1, you can see this table here, and you can see similar table and similar provision on our local code NSCPC 101-15, similar table here. So again, what is specified here on this table is that what is specified here on this table are the limits for us to be able to say that our concrete is already cracked or still uncracked or transitioning from being uncracked to cracked. So again, if you can remember from our very first discussion, we want our concrete element to avoid experiencing cracks. So we don't want our concrete element to experience cracking at service loads condition, or as it carries the service loads. We don't want cracks to occur on our concrete element as it supports its intended service loads that are supposedly be carried by it. So we don't want it to experience cracking. And according to this table, if the tensile stress acting on the concrete element at service loads, obviously, is greater than square root of FC prime, therefore, we can already consider it as already cracked. So in terms of limits in the tensile stress, we can say that our limit at service loads in terms of the tensile stress acting on the concrete element will be this limiting value here, which is square root of FC prime. So that will be our basis if this tensile stress acting here on the concrete element being considered is code compliant or not. So the FC prime again is already given, and if you will compute the square root of FC prime, that is equal to 6.43 megapascal, which is obviously greater than the total stress or actual stress we have computed here. So therefore, that tensile stress we have computed is okay. It is code compliant as well. So therefore, we can take it as the final answer as well. So that is how you can check the uh, the compliance of these stresses that we are computing here on the code, even whether it is in the international code or our local code. But I will recommend that you will check on both, since again, just like what you have experienced a while ago, there are some overlooked small details, like for example, in the case of the FCI prime on our local code, sometimes there are typographical errors. So we all know that there may be an error on the code, especially typographical error. So that's why you have to double check it always on the reference code, which is the ACI. So there, we already understand the C-line method of designing pre-stressed concrete elements. So we are done there. So now we are down to our last goal for this meeting, which is to understand the load balancing method of designing pre-stressed concrete elements.